So, continuing our study of ideals and in the rings of integers of number fields, we're now going to somehow look at all the properties that these ideals satisfy, or that these rings satisfy, and somehow study them in general. So, it turns out that rings of integers are a special kind of a special type of ring called a Dedekind domain, and so to study the ideals in there, we might as well study Dedekind domains because this captures exactly the structure that we care about. So we're going to move into this section. So let me give you a definition. So last time we saw lots of properties of ideals in rings of integers. We saw, for example, that these rings of integers were Noetherian, which means every ideal is finitely generated. We saw that if you take an ideal, if you have an ideal, then it always contains some positive integer in it, and in a ring of integers. And we saw that the quotient of the ring of integers by any ideal is also finite. It's always finite, as long as it's a non-zero ideal. So these properties are common to all Dedekind domains. So here's the definition. Definition 3.3.1. A Dedekind domain domain is an integral domain R such that the following three things hold. One, we need that R is Noetherian. Two, we need that every non-zero prime ideal is maximal. And lastly, we need that R is integrally closed. Remember, this means that R is integrally closed in its field of fractions. So last time we saw that for rings of integers, that the ring of integers is Noetherian, as I was saying, and we saw also that every prime ideal is maximal. So, but we haven't seen the third condition. So here's a theorem. So 3.3.2. If K is a number field, and OK the ring of integers, then OK is a Dedekind domain. Okay, let's prove this. Proof. So let me just give the references. So proposition 3.2.3 gives the first one, and corollary 3.2.6 gives the second one. So all we need to check is that OK is integrally closed. So I just need to check. So I'm going to prove this. So I'm going to take gamma be alpha over beta in K, which I remind you is the same thing as frac OK. So if I take some element in the fraction field, alpha and beta in OK, then let's assume that we have some element like this, which satisfies a monic polynomial with coefficients in OK. Let this satisfy a monic polynomial with coefficients. In OK, then I claim that this is an algebraic integer. Claim by this I mean gamma is an algebraic integer, in which case gamma is in K intersect z bar, the ring of all algebraic integers, and we know that this is just OK. So this is done. So I need to check this claim, but the claim is, so I'm going to reference the exercise in the notes. This is exercise 2.1.18, but it's also one of the exercises in problem sheet 4, I think. Can't remember the exact number, but it was the harder, quote unquote, of the two exercises, of these set of exercises for sheet 4. So I won't do the proof here. There will be solutions to that in the notes, in the problem sheets, so you can go over there and look at it. So great. So our rings of integers are Dedekind domains. So let's look at some properties of Dedekind domains and let's start seeing why we care about this. So some properties of So what do we start? We start with a lemma. Lemma 3.3.3. So the R be a Dedekind domain. Then every ideal contains a product of prime ideals. Later on, we're going to see that every ideal can be written as a product of prime ideals. But we'll start off by just checking that every ideal contains a product of prime ideals. So proof. This is really what we're going to really use Noetherianness quite strongly in part 3 of the Noetherian list. So here, let's assume for contradiction this isn't the case. And I'm going to let S denote the set. Denote the set of all ideals that do not contain a product of prime ideals. So we're assuming that this isn't that this isn't holding. So there exists at least one ideal which doesn't contain a product of prime ideals. So let's we have a set of all of them, and let's consider this. So this is a non-empty set. Now, since this is where it's like magical how Noetherianness works. So since R is Noetherian, if you look at the definition I gave, the third incarnation of this definition, it tells us that S must contain a maximal element. Contain a Don't confuse this with containing a maximal ideal. This element doesn't have to be a maximal ideal. It's just an element which is maximal with respect to the property of not containing a product of prime ideals. So now, let's call this. I'll give this element a name. I'm going to call it frac m. Note that this frac m can't be prime. Can't be prime. Otherwise, m is always contained in m. So we'd have m would contain a product of prime ideals. M times 1. That's a product of prime ideals, which would be a contradiction. Otherwise, this would give a contradiction. Contradict m being in S. Therefore, what does this mean? Therefore, we can find, so it doesn't contain a product of prime ideals. We can find two elements, R and S, in R, remove this maximal ideal, so the set of elements in R which aren't in M, such that RS is in M because it's not a prime ideal. It doesn't contain a prime ideal, so I can find such elements. Now consider the ideals. They're generated by R plus M, and they're generated by S plus M. So this is the sum of ideals. Both are larger than M. And so they must contain a product of prime ideals because M was the biggest ideal which didn't contain a product of prime ideals. These two ideals are bigger, so they can't be in this set S, so they must contain a product of prime ideals. Both are larger than M, so must contain a product of prime ideals. So does their product, so R plus M times S plus M. So don't confuse this notation with quotients. Here I have two ideals and I'm adding them together as the sum of ideals, as we saw in the first problem sheet. I'm not talking about the quotient of R mod M or anything. This isn't a representative of R mod M. This is just sums of ideals. So each of these contains a product of prime ideals. So their product also contains a product of prime ideals. This product is contained in M, since if you expand it out, you'll see that if you use the fact that R and S is contained in M by our assumption, because M didn't contain product prime ideals, so you see that this product, if you multiply out essentially, but then this product is contained in M, and I said that this product contains a product prime ideal, so we've arrived at a contradiction. So we have a contradiction. Okay, great. So it might not seem like a very useful lemma, checking that every ideal contains a product of prime ideals, but it's on our way to checking that every ideal can be written as a product of prime ideals. So we'll see why it's useful later on. Similarly, here's another lemma which doesn't look very useful, but turns out to be more useful than we think. These are just a bunch of technical lemmas. So today it's just going to be like proofs of technical lemmas about Dedekind domains, but we'll see the payoff later. So let R be a Dedekind domain. With field of fractions R, okay. Okay, so I'm not saying this is a number field, just some field of fractions which I'm denoting K. And I'm going to let Goth A be a proper ideal. When I say proper, I mean it's not the whole ring and it's not zero. Then, what am I saying? That there exists some X in K, remove set R, K not in R, such that X times my fraction ideal is contained in R. Okay, so this is another weird one. I'm just saying if I have a proper ideal, then I can find some element in the field of fractions, not in the ring, such that their product is in R. This again, it's just a technical lemma. It's more useful. It'll be useful later on, but at the moment it just doesn't seem useful at all. And the proof isn't easy. This proof is annoying and technical, but the ideas in it are quite useful. So I wouldn't just skip over it just because this is a technical proof. The ideas that we use in this proof will show up later on. So maybe it's worth taking the time. So I'm going to let, because my ideal is proper, I'm going to let A in frag A be a non-zero element. By the previous lemma, 3.3, my 3's lemma, the ideal by A contains a product of prime ideals. So let's take, say we have some product I equals 1 to M of PI is contained in A with PI prime ideals. Here, again, just remember this is a product of ideals. So go back to sheet 1 where we define what product of ideals was. So say it contains a product of prime ideals PI. and we choose it such that m is as small as possible. So let's take the smallest product of prime ideals, which is contained inside our ring M. So from like the first few lectures, we know that every ideal is contained in a maximal ideal. So let's try and leverage this. Since every ideal is contained, and this ideal is proper, so since every proper ideal is contained in a maximal ideal, which I'm going to just denote P for some reason. Again, this follows from like proposition 1.1.22 that we saw really right at the start, that every proper ideal is contained in a maximal ideal. Contains a maximal ideal is contained in a maximal P, which is also, so all maximal ideals are prime, which is also prime. Therefore, what do we have? We have A is contained in my ideal P. So my product of ideals I equals 1 to M of PRs is also contained in this ideal P, because I said A is an element of A, so the ideal generated by A is contained in A. So this product is contained in this ideal A, and this ideal A contains this product, and now this product must be contained in the maximal ideal that contains all of this stuff. So now I claim that. Now we claim that P must contain some one of these prime ideals goth pi. How do I prove this? If not, then take some AI for each I. Take some AI in pi not inside of P. So I'm assuming that these ideals don't contain that. Yeah. If not, then P does not contain any of the PIs. So I can always find an element in Pi which is not in P. I'm going to pick one and call it AI. Then P contains the product over I of these AIs, right? Because it contains all of this thing. So I have to, in each AI lives inside one of these copies of these PIs. So their product is contained in my ideal by this equality here. So it contains this, but by construction, it doesn't contain any of the AI, and this contradicts P being a prime ideal. So it's a maximal ideal which is prime. It has to be prime. So it contains a product of elements but doesn't contain any of the elements, and that can't happen in a prime ideal. Contradicts P being prime. Great. So I know that P contains one of these PIs. So let me just, after some relabeling, I can assume that we have, say, P1 is contained in P, but by, what was it? We know because we're in a Dedekind domain, by definition 3.3.1, in a Dedekind domain, every prime ideal is maximal. So this pi is a prime ideal, n is maximal, and it can't be contained, and it's contained in some other ideal. So these two ideals have to be the same. By the definition, every prime ideal is maximal. So P is this ideal P1. Great. So we're almost there. So I've taken my, just to remind us what we're trying to prove. I pick some proper ideal, and I want to show that there exists some element in my field of fractions, not in my ring, such that x times my ideal is contained in R, in my ring. And how have I done this? Well, I've taken an A inside of my ideal, non-zero, which I can do. And now I've talked about I'm using this fact that this prime ideal that this ideal generated by A has to contain this prime ideal. And I know that this thing has to be contained in some ideal P, and I've somehow deduced that I have my ideal A is contained in P, and A also contains this product of prime ideals. And I know now that this P is exactly can be written as one of these prime ideals. So we're going to start using this as follows. So I'm going to construct the element x explicitly, and it's going to be the element x is going to look like b over a, where a is this element that I've taken here, and b is the element I'm about to construct. So since m, so remember this m, which is this product, I took it to be as small as possible. I took the smallest product of prime ideals contained in A. So since m is minimal, we know that this can't contain any smaller product of prime ideals. So we can find some element B in the following set, which is take the product from I equals 2 to m of these PIs and then remove the ideal A. Right? This is a product of less prime ideals, so this can't be contained in A. So I should be able to find some element in here which is not in A, and I'm going to call this B. Great. So now the claim is that taking x to be b over a, we get the result. I.e., if I multiply x by my ideal frac A, or goth A, something it's called, then you stay in the ring R. So let's prove this. First, note that x is in K and not in R, since otherwise we have b over a equals c, some element in R, then b would be a times c, which is contained in the ideal A, which, if you just realize, I took a b such that it wasn't in this ideal A. This contradicts our choice. Contradicts choice of b, so this can't happen. So my element lives in the right set. It lives in the fractional elements, but not in the ring. Now, we claim that, what's the thing I need to finish off? That this is contained, x times a is contained in R. So how do we do this? To see this, note that since we have the following, we have b times my fractional ideal p. This is contained in the product from I equals 1 to m of these PIs, which is contained in A. Remember, b was some element in this product of the other things which weren't in A, and p was the same thing as p1. So b times p is contained in this thing, and we were assuming that this product is contained in this generated by A. So we have this chain of inclusions. So since we have this, we have x times p is contained in R. Why is this the case? Well, x is b over a, and I know that b times p is contained in the ideal A. So every element in b times p looks like some element A times some other element of my ring. So I can divide every element in here by A. That's what x looks like. So what you're left over with is some element of R. So So since we have this equality, we have x times b is an R, and since A is contained in the ideal P, we have, now if we just link this up, we have x times A is contained in x times P, which is contained in R, and this is what we wanted to check, that x times A was an R. Done. So that's a long proof of a technical lemma, but it will pay off for us. And the first place it pays off is in the next theorem, which I'll finish off this part 1 with, which is the following. So theorem 3.3.5 says the following: let R be a Dedekind domain. And frac A in R an ideal. Then there exists an ideal B such that A times B is principal. So understanding when ideals are principal is going to be an important thing for us. Turns out that if all of your ideals are principal, then your ring has to have unique factorization. PID is a UFD. So this is something that we'll care about. But these technical lemmas that we had before actually allow us to prove this for general Dedekind domains. So let's do the proof. So I'm going to let alpha be some element in A, take away not 0. Maybe I should say proper ideal. Maybe from now on, I'll probably always be proper ideal. Proper ideal. So pick some element like this, and I'm going to let me tell you what B is. I'm going to let B be the following. It's going to be the set of all beta in R such that beta times my ideal goth A is contained in the ideal generated by alpha. Okay, so I take all elements in R so that when I multiply my ideal beta by my ideal A by beta, I land inside this ideal alpha. And claim that this thing is an ideal. And well, this isn't hard to check. Go through a definition and you'll see that this is an additive group, and it's closed. If you have one element of it in it and you multiply by some other element, then you stay inside the ideal. So I say it's easy to check this is an ideal. This is an ideal, and it's non-zero since alpha isn't 0. Yeah, the element 1, not the element 1. This alpha isn't 0, so just pick 2 elements inside of this ideal generated by alpha, and this will work. So by definition of beta, we have the following. We have the product of these ideals is contained in alpha. We call this equality dagger. We have this inclusion, and I just claim that we actually have an equality, that the product of these two ideals is exactly alpha. We claim that this is an equality. So maybe it's a good time to point out in the notes, sometimes I write, A contained in B, and sometimes I write A something like this. It's just laziness. These two symbols mean the same thing to me. I know it's bad notation, but if I want to highlight that the two things aren't the same, then I'll explicitly say that they're not the same. Otherwise, you can take this to be the same thing as this. I allow equalities. I'll say explicitly if it's not the case. So in case you go through the notes and start don't worry too much about the inclusions. Unless I've said something about them, then just assume that they can be subset equals. So we claim that this is an equality. So consider the set. And note goth C. It's going to be 1 over alpha, the product of its ideals. This is a subset of R by dagger. I know that the product of these two ideals is always contained in the ideal generated by alpha. So every element in this thing is divisible by alpha. This is what this means. So if I take any element here and divide it by alpha, I'm just left with an element of R. So this is a subset of R by this condition. And you can check that it's in fact an ideal. It's in fact an ideal. So now, if C wasn't the proper ideal, if C equals the whole ring R, then we're done. Then A times B equals alpha. Just imagine, this is R. Somehow you can do this multiplication of ideals. You can just multiply up essentially on both sides, and you'll get this equality here. This somehow works if you're careful enough with your ideals. So if this is the case, so we are done. So let's assume that this isn't the case. So assume, let's go to the next line. For contradiction, that C is a proper ideal, or it's just not the whole thing. Then what can we use the previous lemma? Then by lemma 3.3.4, we can find some x in k. Did I say what k was? No, some x in k, not r. Here k is frac r. Looks like an x. K is a fraction field of r. And what's the property that this x has? And x times c is contained in R. This was my what this lemma was telling me, that I could find an element in k, not in R, such that x times c was in R. So now, note that C contains the ideal B, since alpha is an element of A. So look at this definition. Alpha is in A, so if I pick the element alpha in A, then this will cancel out with my denominators, and I'm just allowed with I'm free to choose any element of B. So the fact that alpha is an A tells me, just check it by hand if you don't believe me, that B has to be contained in C. Therefore, x times B, this is contained in x times C, which is contained in R, by just chaining up these equalities. Moreover, since x times C, this is x over alpha A times B, and just using the definition of C up here. And we have that this thing is in R, we have x times, all right, I'll just write it like this. That multiplication of ideals is commutative. So I've swapped the A's and B's around in here. But this is contained in the ideal alpha. Since this is the case, just notice I have x. X over alpha times AB is an element of R. Somehow again, just multiply up. Imagine that I'm multiplying up by alpha and then taking ideals again. Now then you get x times B is contained in the ideal generated by alpha. So we have this this inclusion. So now, looking back at the definition of the ideal B, we see that since we know that x times b is contained in R, we have x times b is contained in B. Just notice that, what did I take? I took B to be the set of all elements in R such that when I multiply them by A, I ended up in alpha. And what I've just shown is that x times B, whatever all the elements of this set, when I multiply them by A, stays inside alpha. So by definition, what B is, x times B has to be contained in B. So we have this this inclusion. So x times B is in B. So now, this is, if you think of x as multiplication by x as like a map, then we can study this map and arrive at a contradiction. So I'm going to let beta 1 to beta n be a basis. So this is an B is an ideal, and it's finally generated, so I can find a basis. Well, I'm going to say a generating set. Generating set for B. We can use that x times B is contained in B to think of multiplication by x on B as a matrix. I'm going to call AX. This is very similar to like the standard representation definition, right? We had a matrix attached to the map, which was multiplication by x. Matrix defined by, so this matrix defined by x times B1, B2, beta n. Is AX times beta 1, beta n. So this this matrix is just defined to be the matrix you get by thinking of what x does to multiply to the basis elements. This is a n by n matrix over R. And if you think about what this definition, with eigenvalue, well, with x as an eigenvalue, right? I have my matrix times a vector is x times a vector. So this is x is an eigenvalue for my matrix. This means x satisfies some monic polynomial. It's an eigenvalue. It satisfies a monic polynomial over R, which I mean coefficients in R. But we're in a Dedekind domain, but R is integrally closed. So x is in R, but this is a contradiction because which contradicts x being in K, not R. Remember that we took the lemma told us I could find, where was this that I used it? Yeah, lemma 3.3.4 told us that we could find an x in the field of fractions, not R, such that this happened. I found it. I used my x. I did all of this this working and this deduction, and now I've gotten to a contradiction because I checked actually x would have had to be in R. So this can't have happened. So we reach a contradiction. So this completes the proof. So why did I contradict? I contradicted the fact that C, this ideal C, wasn't the whole ring. I said, assume for contradiction that C is a proper ideal, so not the whole thing, and now I've arrived at that contradiction. So in fact, yeah, A times, this C is a full ideal, and we saw that implied that A times B was the ideal alpha. So for every ideal, I can always find some other ideal, which I multiply them together and I get a principal ideal. And this is great. This is going to lead us on to definition of fraction ideals, and eventually we're going to form a group out of these ideals, and like the principal ideals are going to somehow act like our identity element. This is called the class group. Okay, I'll finish here for now.